first, can we start with the trig identities?
Sure. Which ones? There's a lot of them. Want to just go over all of them, or?
Let's do the list here. It says Pythagorean, cofunction, addition, subtraction, double.
Okay.
There's a lot.
Okay. Yeah. So start with the first one.
Pythagorean.
Okay. What's the primary Pythagorean identity?
What's a primary?
Well, by primary, I mean the first one they teach you.
Oh, so that'd be a squared plus b squared equals c squared?
No, it's sine squared plus cosine squared.
Oh.
What's that always equal to?
1?
Yep. Now, there's one that involves tangent. And the only way to remember this is to memorize it. What is it? It's tangent squared plus 1 equals secant squared. Okay?
Okay.
The third one is the same as the second one, only using the cofunctions.
Well, hold on. Is that tangent squared x plus 1, does that equal secant squared or secant squared x?
Excuse me. I left off.
Okay.
Yeah.
Thank you.
In other words, it's different than this. That means that secant squared minus tangent squared is equal to 1. Right?
Okay.
Okay, so you have to memorize this separate. It's not related at all. Both of those you need to memorize. There's a third one that you don't need to memorize because it's the second one only using the cofunctions. So what would it be? What's the cofunction of tangent?
Cotangent.
What's the cofunction of secant?
Cosecant.
Yeah, that's what cofunctions are. Stick the co in front of the word.
All right.
Okay, that's all it is. So the third one is the same as the second, only using cofunctions.
Okay.
Okay. What was next on your list?
So that was the cofunction thing then.
Okay, well, that's pretty easy. What's the cofunction of sine?
Cosine.
What's the cofunction of secant?
Cosecant.
What's the cofunction of tangent?
Cotangent.
What's their relationships? They all share this same relationship. Think about the sine of 60 degrees, or the sine of 30 degrees we know to be 1/2. Right? Well, the cosine of 60 degrees is also 1/2. So if I substitute 30 here, I get the sine of 30 degrees equals the cosine of 60 degrees. Same with all three of these cofunction relationships. This is the most important part of the cofunction relationships. And vice versa. In other words, cosine of x is equal to the sine of pi over 2 minus x. Okay?
Okay.
So there are 6 cofunction relationships, 3 for each, or 2 for each of the 3 pairs.
Okay.
Okay. Now, what was next on your list?
Addition.
Sum and difference?
I guess like there's addition and then the next one's subtraction, so I guess.
I generally refer to this as sum and difference. I write it like this. And it applies to whether it's being added or subtracted. And I start with this one, and there's a reason. This one's the easiest one to memorize. It's cosine, cosine, opposite, sine, sine. So it's cosine of A, cosine of B, opposite of that, which is minus plus, and sine of A, sine of B. The next one to memorize is the sine sum and difference. And it's similar to this in the fact that it's going to end up with two sines and two cosines in it. The sine is going to be the same, not opposite. And if I'm going to end up with two sines and two cosines, what must it look like?
Cosine A, sine B, sine A.
Yeah, I always start out with sine, but the next thing is cosine and changes that. In other words, it's not sine A, cosine A. It's sine A, cosine B. Same thing over here, only opposite, right? So what's the rest of it?
Sine B, cosine A.
Yeah. So, I don't know. It seems to me that if you memorize that first, the second one is all you have to do is realize you're going to have two sines and two cosines. The middle sign is the same, and there's really not very many other ways to write it than this. Okay?
Okay.
Tangent of A plus or minus B. Now, this is, tangent is sine over cosine. So theoretically, I could take this and divide it by that to come up with my answer, but that's not the way we memorize it. The way we memorize it is tan, the numerator looks exactly the same. The denominator has a 1 opposite sign, and in the product, tan of A times the tan of B. Okay? I think that's correct. You have a book in front of you? Probably better if you don't.
Okay.
Let me double check, make sure I got it right. And the only reason I say that is if you're trying to memorize stuff, you're better off not always referring. Oh my goodness.
Well, I do get a note card for the final. So.
Oh, okay. All right.
Yeah, I'm writing a lot of the stuff down here. So.
All right. If you get a note card, then yeah, we don't really need to work on your memorization techniques. Wow. Yeah. Let's see. What was next on your list after sum and difference?
Double and half.
Okay. Let's talk about double angle. The easiest one is this one. That's just 2 sine cosine. Okay? This one is hard because there's 3 of them. Of the 3, one is a function of cosine and sine. The other is 2 sine squared x minus 1, I believe, and the third one is 1 minus 2 cosine squared x. Or do I have it backwards? This one I better look up. Unfortunately, my book fell and I don't know. Oh, here I got it. I think I got it. Yeah. Okay. Okay, I did the tangent one correct. Now let's go to angle. Okay, cosine is 2. I did do it backwards. This one is correct, but the second one is 2 cosine squared minus 1, and the third one is 1 minus 2 sine squared.
Okay.
One of the keys to memorizing this is it's negative in all three. It's minus there, minus there, minus there. I suppose you could say the cosine goes first in the top two, and in the bottom one, the sine comes last. Maybe that's a good way to memorize it.
Is there a double thing for the tangent?
There is, but let's talk about which one of these three we use, because that's going to be the harder question.
Okay.
It depends on the application. If I have something like the following, cosine of 2x plus cosine of x equals 3, and I want to solve that equation, which of the three identities am I going to use? First, second, or third?
You'd use
this one because I will now have a quadratic in cosine of x. I can solve it using the quadratic formula. If this was sine, well, now I want to make a quadratic in sine x. So I'm going to use this identity. In other words, I'm going to turn my cosine of 2x into this, and now I'll have everything in sine x. I'll have a sine squared, I'll have a sine, that's a quadratic. The key to solving trig equations is to get everything in the same trig function. It's very difficult to solve a trig equation if you have a mixture of trig functions or if you have a mixture of what's inside. What you want is to have the same trig function and the same argument. In other words, x, not 2x. Okay? So that's what determines which identity you use, is what you want to turn the equation into. I want to turn this into an equation of sine. I'm going to use this one. If I've got a cosine there, then I want to turn it into an equation of cosine. Nothing but cosines, I'm going to use that. And there are some situations where you'd want to use that. In other words, if I had cosine of 2x plus sine squared of x, well, now if I use this one, the sine squareds disappear and I'm left with just cosine squared of x. So which one you use depends on what application you're trying to do with that identity. Okay. Tangent of 2x. Well, I guess the immediate question you would say was, well, tangent of 2x is sine of 2x over cosine of 2x, but which identity do I use to figure it out? Well, you don't have to figure it out. There's only one for tangent of 2x, and it's 2 tan x over 1 minus tan squared x.
Okay.
Not that, and I tell you a good way to memorize this, if you think about it, that's the same as tan of x plus x, right? Well, in my sum and difference formula, that would have been the tan of x plus the tan of x all over 1 minus the tan of x times the tan of x. Notice that's the same thing as this.
Yeah.
2 tan x's I get, and multiply them together, I get tan squared of x. So if you forget the identity for tan of 2x, just pretend it's x plus x, and you'll get it. What's another one after that?
The half identities.
Half angle, okay. These are square root of 1, I think it's minus cosine of x, all divided by 2. And the cosine of x over 2 is the square root of 1 plus cosine of x all over 2. I might have those backwards. Let me look them up. Nope, I got it right.
Okay.
The tan of x over 2 is equal to the square root of interesting. They have 3 for this one. I never knew that. That there were 3 identities for the cosine for the tan half angle. The first one is kind of the obvious one, because tan is sine over cosine. So if I put this over this, the 2's go away, and I end up with the square root of 1 minus cosine x over 1 plus cosine x. There are 2 others, but I don't know why you would ever need the others. In other words, the only thing I need to figure out the tan of a half angle is what the cosine of that angle is. And the others they give are mixture of cosine and sine.
What are they?
What are they? Okay.
Yeah.
Yeah. Well, the other one is, interestingly enough, no radical sign. That could be helpful for doing it. And the bottom one is kind of the reverse, the reciprocal, whatever you want to call it, 1 plus cosine x. So these are the 3 identities for the tan of half angle.
Okay.
And this first one is actually plus or minus. Don't want to leave that out. In fact, it's plus or minus on all 3. This is plus or minus also, and that's plus or minus. And usually when you're doing problems regarding these, you can figure out which one to use, the plus or the minus. And it's only one. You have to figure out which quadrant you're in, things like that.
Is it plus or minus for the tangent as well?
Yes.
All 3 of them?
No, just the top one.
Okay.
Yeah. Okay. It might be worth knowing all 3 then, because you wouldn't have to worry about the plus or the sign on these 2.
Okay.
Whereas you are going to have to figure out whether to use the plus or the minus for this one, depending on which quadrant you're in. Okay. That's all for your identities, right?
Yeah.
Okay, let me give you a test.
All right.
It's the tan of 75 degrees.
Oh,
So what's x going to be?
Well, for this, what I want to do, one of those things where I would find like a 30-degree angle or something.
There you go, right there. In other words, I'm going to write the 75 degrees as 150 divided by 2.
Okay.
Now I can use the half angle formula for 150 degrees. So let's try the first one.
So that would be plus or minus the square root. Okay.
It's going to either be plus or minus. What is it going to be? Let's figure that out first. It's not both.
So would that
not both. It's depending on what quadrant we're in. Which quadrant are we in?
It's the first quadrant?
Yes, it's this quadrant, first quadrant. So it's definitely the plus.
Okay.
If we were in the second quadrant, we'd choose the minus. Now, what goes in here?
That'd be 1 minus cosine of 150 over 2.
Well, not over 2. It's over 1 plus cosine of 150. In other words, the 2 only comes in when we're doing sine or cosine half angle. Notice the 2? And that 2 is inside the radical. It's not outside the radical. In other words, this thing comes all the way down like that in both cases. Okay? But we're doing tangent, so the 2's went away, and all we have to do is figure out what that is. Well, what's cosine of 150?
Should I get my calculator for this?
No. Think of it as your unit circle. What's the equivalent first quadrant angle?
So that would be the 30 degrees.
Okay, what's cosine of 30? Square root of 3 over 2.
Oh, okay.
But what's the sign on cosine of 150?
1/2.
No, the sign being plus or minus, it's minus.
Oh, okay.
Right? In other words, cosine of 150, this gets a little confusing because this is in the second quadrant, which is fine. Our original problem, we're definitely looking at a first quadrant angle. We know the tangent of 75 degrees is going to be positive. Whatever it is, it's going to be positive. Well, when I use this formula, I have to talk about the cosine of 150. Well, cosine's negative in the second quadrant. So it's the same as the cosine of 30, only negative. So it's negative root 3 over 2. That goes in the numerator. In the denominator, I have 1 plus a negative square root of 3 over 2.
Okay.
So that would be your answer. The square root of 1 plus square root of 3 over 2 divided by 1 minus square root of 3 over 2. And then there's more tough algebra to be used here. In other words, we have to do this manipulation. We do it by finding a common denominator of 2. And then we'll combine our fraction divided by our fraction into a single number. Let's do that. Let's make sure you can do that. What's the numerator going to be?
So so I changed the 1 into something over 2. So it'd just be 2
over 2. So it now becomes 2 plus root 3 over 2. So that's what I get when I do this operation. The bottom becomes 2 minus root 3 all over 2. And now I can flip and multiply. So the 2's go away. So effectively, I end up with this in the denominator, this in the numerator. Ooh. Yeah, I can do that. If they're, yeah, that's what I get.
Okay.
That's what the tangent of 75 degrees is going to be. Okay, so the identity for tangent, the easiest one to work with is this top one, because you only have to figure out sines and cosines. Notice the other two identities, I would have had to figure out what the sine of 150 degrees was also. So this is the one you almost always use, because you only have to figure out what the cosine of that x is. And x is always going to be twice the angle that you're looking for. In other words, if I made this be 30, then x is going to be 60 divided by 2. Or 30 degrees would be represented as 60 divided by 2. I wouldn't need to do that for the tangent of 30 because I know what that is. But I didn't know what the tangent of 75 was. So it's a useful technique when you have angles that you don't know what their results are. By using the half angle or the double angle, you can figure out trig functions of odd angles. By odd, I mean not your standard 30, 45, or 60, or multiples of those.
Okay.
What else besides trig identities and stuff? I mean, there's a lot of material to cover. You're going to have to kind of direct.
Yeah, the next thing's the law of cosines.
Okay. What's the law of sines?
Sine A over sine A over A?
Over little a.
Yeah, equals sine B over sine, or over B.
Over little b. In
Yeah.
other words, little a is the side opposite angle A. Little b is the side opposite angle B. Okay. You use this, the law of sines, whenever you have, let me draw a couple triangles here, and I'm going to ask you which to use, the law of cosines or the law of sines.
Okay.
What do I use there? They're always going to be giving you three pieces of a triangle. Given three pieces of a triangle, you can solve them using either the law of sines or the law of cosines.
I would use the law of sines for that one.
Because I have this relationship. As long as I have one of those relationships, I can solve the entire triangle by the law of sines. But if I make this side 6 down here, now I still have three pieces of information, but I no longer have an opposite side angle relationship. In other words, I cannot specify any of these three for this triangle. This is side, angle, side. When you have side, angle, side, you use the law of cosines.
Okay.
The only other situation you use the law of cosines is if you have three sides. In other words, if I have all three sides, I don't have that angle opposite side relationship. These are the only two situations where you start off using the law of cosines. And incidentally, whenever you start off using the law of cosines, you have to finish it using the law of sines. Okay, so you never solve a triangle entirely with the law of cosines. You need the law of sines to get the piece of information. So, the law of cosines. Basically, think of it as kind of like the Pythagorean theorem.
Okay.
Start with c squared. What's c squared equal?
A squared plus b squared.
We're going to start with the Pythagorean theorem, and then we're going to start subtracting stuff from that. What am I going to subtract?
Sorry, can you give me 1 second?
Yes.
Sorry, my cat wanted to leave.
Okay. So, the secret here is to memorize it like it's the Pythagorean theorem. Subtract 2 times a times b times the cosine of which angle?
C?
Always whatever that letter is. This is a capital C, this is a little c. Okay? So there's one law of cosines if you're trying to solve for C. If you're trying to solve for A, well, how would it go? It's exactly the same pattern. It's the other two. So what would it be?
Would it be c squared minus b squared, or would it still be
plus c squared?
Okay.
In other words, it's always the other two letters minus what?
2bc cosine A.
There you go. And the final one is if you were solving for b squared.
That would be a squared plus c squared minus 2ac cosine b.
Correct. Okay. Now, let's do one because it's not that obvious as to how you do it if you have 3 sides. Okay? I want to solve this triangle. Where do I start?
So you do 5 squared equals 9 squared plus 7 squared minus 2 times 9 times 7 times the cosine of C.
Okay. Now notice there's one variable in that equation.
Yeah.
So we have to isolate cosine of C. So what do we have? We have 25 equals 81 plus 49 minus 126 cosine of C. Move these two to the left. So that's 130 gives us minus 105 equals minus 126 cosine of C. What next?
Cosine C equals negative 105 over negative 126.
Which is positive.
Yeah.
This number is less than 1, we're okay. Had this number been greater than 1, I'm dealing with an impossible triangle.
Okay.
Okay? How do I get angle C?
Just take the, would you do the inverse cosine of that?
Yes.
Okay.
That gives me one angle. Let's say that angle comes out to be 50 degrees.
Would I need to be in degree mode for that to work? Or like on my calculator?
No. Well, yeah, you do. If you want it to come out in degrees, you need to be in degree mode. You could be in radian mode, but then the answer it's going to give you is going to be radians.
Okay.
Since usually when you're solving triangles, you don't use radians. Because the whole point of solving them is to come up with all 3 angles and all 3 sides. So step 1 gives us one angle. And notice you didn't have to start with 5 squared. You could have started with 7 squared, and we would have solved for angle B. Or you could have started with 9 squared on the left, and we'd be solving for angle A. The point is, you can start any side you want, and first step, you get this angle. Now, to finish solving it, I now have a side and its opposite angle. I can finish it using the law of sines. In other words, to get angle, once I have this relationship, that is a fixed relationship in that triangle. In other words, 5 over the sine of 50 degrees, and I can reverse these, they don't always have to have the sine on top, that's equal to 9 over the sine of A. Well, there's only one variable. I can solve for A. Once I've solved for the second angle, I don't need to use the law of sines to solve for the third angle. I just know that they're going to total 180 degrees. And so I just add the two angles together, subtract from 180 to get the third one. And that's typically the way you do when you have to use the law of cosines. You solve for one angle, and then you solve the law of sines for a second angle, and then you use the fact that all three angles have to add to 180 to get the third angle. Let me change the problem slightly. Now I'm giving you 3 pieces of information, but it's side, angle, side. So again, I cannot begin by using the law of sines. You can't use the law of sines until you have at least one fixed relationship. So, using the law of cosines, what's the first thing I'm going to use? Which of the 3 formulas am I going to use?
I would do c squared.
Yeah, because I know this angle.
Yeah.
And that's going to allow me to have the only unknown is going to be on the left. I know what a squared, a squared is 9 squared. B is 7 squared. Well, I know A and B. And the cosine of 50 degrees. So all of my unknowns are on the left side now. So when you're solving a side angle side problem, you do need to pick one of the 3 formulas to use. It's slightly different than when you have side, side, side. When you have side, 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 you can choose to start with any of the 3. But when you have side, angle, side, always start with the one where you're going to be able to figure out the cosine of that angle. All right. Again, with both the law of sines and the law of cosines, if you ever find yourself facing something like this, impossible triangle.
Okay.
Because sines and cosines have to be between 1 and negative 1. They can't be greater than 1, they can't be less than negative 1. Same thing if you find this. Impossible triangle. What makes a triangle an impossible triangle? Well, the basic rules of triangles is any side has to be less than the sum of the other 2. So I could not have a side of 17 right there, because it's not less than the sum of 7 plus 9. So if I gave you this triangle and said, solve it, it's side, 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 solve it, you would use your law of cosines, and you would discover that the cosine of one of these angles, the very first one you look at, is going to be a number greater than 1.
Okay.
And that's in other words, you don't have to figure out if that's a possible triangle or not. Just go ahead and apply the law of cosines, and it'll tell you if it's impossible. Now, there is one difficult problem for the law of sines, and that's the ambiguous case of the law of sines.
Okay.
You want to go through one of those?
Yeah.
Okay, let me give you the example that I'm very familiar with, where we have a 30-degree angle, we have a side of 10 there, and we have a side of 8 here. This is side-side angle. Okay, 3 pieces of information. It's not side, angle, side. So I'm not going to use the law of cosines on it. I'm going to use the law of sines. But there's a hitch. There's 2 possible triangles here. One where that angle is that way. The other one, the 8, is right there. Notice that in both cases, it's still 30 degrees, side 10, side 8. So if I merely give you 3 pieces of information and it's angle, side, side, there is usually the possibility that there are 2 answers. There's 2 possible triangles that work. Well, how do we figure out what they are? Let me show you the easy way. Start off by trying to solve it. Go ahead.
So do sine of 30 over 8 equals sine of b over 10.
Okay, the sine of 30 is 1/2. So what's the sine of b equal to?
5 over 8. Is that right?
Uh-huh.
Okay.
Now tell me what b is equal to.
The inverse sine of 5 over 8.
Go ahead and do that on your calculator.
Okay. It's 38.68.
I'll just round it off to 38 degrees. Now,
Yeah.
we know that sine is also positive in the second quadrant. So what's the other possible angle for b?
So that'd be 180 minus 38, right?
Always figure out both. Now, can we have a 142-degree angle for b? The answer is yes, because 142 and 30 do not exceed 180.
Oh, okay.
That's why you always figure out both angles, and then you check to see whether this is a possible one or not. In other words, had this started at 39 degrees, let's just pretend the math is all the same. Well, if that's a 39-degree angle, I don't have room for a 142-degree angle there. That would exceed 180. So I would say, no, that's not one of the possible solutions. But as long as the only known existing angle we have is that 30-degree angle, then that means there's 2 possible solutions. One is 38 degrees here, which leaves 112 here. And the other solution would be 10, 8, 30. And this angle is 142, leaving 8 degrees for that one.
Okay.
And so you would have to give both answers. In other words, this is a completely different triangle than this, but it does share the angle side side. In other words, both of them would be defined. The way you usually get these problems is they're going to give you angle A equals 30 degrees, side A equals 8, and side B equals 10. So they'll give you those three pieces of information, and from that, you know that potentially you have a ambiguous answer. And it's only going to be possible if this angle is less than 90. If the problem starts out that angle is 91 degrees, you do not have to do this step. You still use the law of sines to solve it, but there's no longer any possibility that it can be an ambiguous. Because whatever angle is supplementary to that is going to be bigger than 90 degrees. Added to that, it's going to be bigger than 180. Okay? So the only time you have to consider the ambiguous case is when you have a specifically angle side-side and the angle is less than 90. Then the easiest way to handle it, I believe, is this method here, where you always come up with both angles, the first and the second quadrant angle. Notice why this works. The sine of 38 degrees is the same as the sine of 142 degrees, right? They're both positive. They're first and second quadrant. They're both positive, and they're the same answer. So this does not violate the law of sines. In other words, the sine of 142 over 10 is the same as the sine of 38 over 10. Because at first glance, it would appear that we're violating the law of sines by having both of these triangles work. But we're not. All right, that's the only tough aspect of law of sines and the law of cosines, is handling the ambiguous case. Problem is that I've got one book that gives you an entire page to memorize as to what will constitute an ambiguous case. And rule number 1 is this has to be less than 90. Rule number 2 is this side has to be greater than the sine of this multiplied by that, or some super complicated rules. And I got tired of trying to memorize them, and I went to another book, and it gave me this new technique to use, where I don't have to memorize anything. I just have to solve it, and always come up with this supplementary angle, and then see whether or not it can exist. Okay. All right. What else? We got about 10 minutes. What else would you like to cover in 10 minutes?
Next one is areas of triangles.
Okay. Based on non-right triangles, right?
Yeah, I'm assuming that.
Well, the area of a regular triangle, if it was a right triangle, would be this, right? Well, that presents problems here because I don't know what the vertical is. So if you do the math, you end up with it's equal to 1/2 of your two sides, b times c times the sine of a. Okay. Now, how do I memorize that? Well, pretend it's a right triangle. And I know this side, and I know this side. Well, I know that my area is going to be 1/2 10 times 8 times the sine of this angle, but the sine of 90 degrees is 1. So that tells me that that's the right formula. Because this formula works for a right triangle also.
Okay.
For a non-right triangle, this number's always going to be less than 1, right? The sine of that angle, the known angle, is always going to be a number less than 1, which we need because clearly this distance here is less than 10.
Is there another formula for side, side, side?
I don't think so. There's 3 formulas for area, but they're all, one is B times C, the other is A times B, the third one is A times C. And it's always the sine of the angle that's not these 2 letters. In other words, my 3 formulas are, and I hesitate to even use the capital A there, because we're not talking about angle A, we're talking about the area. So it's 1/2 A times B times the sine of C, or 1/2 A times C times the sine of B, or 1/2 B times C times the sine of A. So as long as these 3 letters are all different, that's how you do it.
Okay.
Okay. And it looks like, from the way I've written it, and I guess this is true, I hadn't realized this before, but you can only use this if you have side angle side.
Yeah, that's why I was curious if there was...
because when I drew it before, I put the 8 over here. Well, it's not going to work if that's all I know. If the 8's down here and I have side angle side, then I can use this formula.
I remember something like there was another formula. I can't remember what it was, but you would find a constant.
Heroes. Heron's formula.
Yeah.
Where the area, and this does work if you have side, side, side. Yeah, it's the square root of the semi-perimeter times the semi-perimeter minus one side times the semi-perimeter minus the other side times the semi-perimeter minus the third side. I'm not sure I got that right. Let me look it up. It's close. I'm not even positive where in my book it is, but let me see if I can find it. Yeah, it's got to be after the law of cosines. Okay. Yeah, I got it right. It's, yeah, I got it exactly right. It's the square root of S being the semi-perimeter, in other words, half of 22. S.
Oh, so would we
11.
just, to find S, do we do 6 plus 7 plus 9 over 2?
Yep.
Okay.
So S is 11 times 11 minus 6 times 11 minus 7 times 11 minus 9. That would be the area of that triangle. Yeah, I wouldn't be able to use one of those other formulas because I don't know any of the 3 angles. So if I don't know any of the 3 angles, this is really the fastest way to figure out the area of that triangle, if it's not a right triangle. And that actually has, I've seen one book call it Hero's formula, and I've seen another book call it Heron's formula.
Okay.
So either of those names refers to this. Yeah, in fact, this book I'm looking at now calls it Heron.
Okay.
Well, any last questions or doubts?
I'm looking through
Problem is you
here.
don't know what your doubts are until you look at
Yeah.
something, yeah.
Oh, how about, is there like a formula for arc length? That one always trips me up.
Yeah, arc length is r times theta as long as theta is in radians.
Okay.
And how can I remember this? Well, if you look at a circle and you consider the entire circumference to be an arc length, well, we know what the circumference is. It's 2 pi r. Well, what would theta be for a full circle? It would be 2 pi in radians.
Okay.
Okay, so this is the formula in radians. If you're in degrees, then you got to convert that to radians by multiplying it by, let's see, if you're in degrees, you want to multiply it by pi over 180. So this is the formula if it's in degrees. This is the formula if it's in radians for arc length. There is another way to look at arc length that I've always done, and I find it easier. I want the arc length of that. What percentage of the circumference is that going to be?
That'd be
1/12.
Oh.
So if I wanted this arc length, let's just figure out the circumference of the circle. Well, that's 2 pi r. That's 6 pi is the full circumference of the circle, multiplied by 30 divided by 360. That's the percentage of the circle that we're looking at. 1/12 of it.
All right.
So this arc length would end up being pi over 2. And this, to me, works a little bit better because you can handle all arc length problems and you can also handle area of sector problems. In other words, the area of that sector is going to be 1/12 the area of the circle. The area of the circle is 9 pi.
Okay.
So the area of that sector is 3 pi over 4. And I didn't have to use the formula S equals R theta for either problem.
Okay.
I just had to figure out what percentage of the circle I'm looking at. So either one of those. One last thing about trig. Let's just cover it before I forget.
Okay.
What are each of these equal to?
Negative sine x, negative cosine x, and negative tangent x.
These are odd functions. Because they're odd, the function of a negative variable is the same as negative the function of the variable. Cosine is even. Cosine of negative x equals cosine of x.
Okay.
And the reciprocals share the same odd-even property. So if I'm talking about the cosecant of negative x, then it's also equal to negative cosecant of x. It's also odd. If sine is odd, its reciprocal has to be odd.
All right.
Same thing with secant. Secant of negative x is secant of x. So the only three you really have to memorize are the sine, cosine, and tangent. The only one you really have to memorize is the cosine. It's the only one that's strange. In other words, those follow, but the cosine of minus x being equal to the cosine of x, that's a little strange, but true. All right, Daniel, good luck on your final. What kind of grade are you carrying right now in the course?
Right now I have a 59 about. So
you need to boost it a little bit with this final.
Yeah.
Okay.
Yeah.
All right. Well, good luck on it. And then you're a junior, right?
I'm a senior.
You're a senior. Okay.
Yeah.
Well, are you going to college next year? Where are you going?
Yeah. I'm going to University of Hawaii.
Hawaii. Wow.
Yep.
I worked at the University of Hawaii bookstore when I was 19 years old.
Oh, wow.
I did. That's one of the most beautiful campuses. I envy anybody that's going to college there. That's got to be a fun place to go to college. But when you get there and you take calculus next year, which you probably will, but if you take any higher maths and you need help, we can certainly do it just the same way we're doing it now.
All right, cool.
Okay? Well, good luck. And enjoy.
Thanks.
That should be fun.
Yeah.
On there.
How much do I owe you at this point?
I'm going to have to figure it out. I did get the check for 180.
Okay.
Seems to me that there might be 2 or 3 sessions after that. So it's either probably going to be 72 or 108. I'll send you an invoice. I've got your email, I think, don't I?
Yeah.
Yeah, or I got your phone number. So
Yeah.
I'll send you a note as to what it is.
Okay.
I'll have to go through everything. I don't want to give you an incorrect figure
Yeah.
until I do the accounting. All right? Daniel, have a good summer, a good college, and good luck on your test tomorrow.
Cool. Thank you.
All right. Bye-bye.